Hello everyone, this is a short video on assignment 2 and the purpose of this video is to provide you some hints and help in solving assignment 2. Assignment 2 at this point is currently open, you can still solve it, and given that the course is becoming slightly more intense and more involved, we thought it will be beneficial for you if we can provide some hints on how to go about solving the questions in assignment 2. So this lecture is for that purpose. Okay. So, let us begin. So, if you look at the first question in assignment 2, it involves the delta function, and the delta function is really quite a complex idea if you want to define rigorously and carefully and use it. So, what most electrical engineers do in practice is to have a rough idea of what the delta function is and how to use it. In fact, how to define the delta function is an interesting question to ponder about. Different books define it in their own way, and we believe the best way to define delta functions is to do the following. If you want to define a delta function, the Dirac delta function, the best thing to do is to define it using this property. You say for any continuous function f of t delta of t dt equals f of 0. Okay. So, this is known as the shifting property of the delta function, and this turns out is kind of a decent way to define it, and this is the most important critical property of the delta function that one keeps using repeatedly in many applications. There are many dangerous definitions you will see in the text, and it is good intuitively to think of the delta function in various different ways, but if you want to be rigorous about it, it's very hard to define. So, so a good strategy is to be aware that the delta function can lead you into the wrong path very easily, but nevertheless it's a very powerful thing to use, and in electrical engineering particularly we use it quite often in a formal way. We use it, and most of our formulas work with the delta function treated more or less in a normal way. So, just be aware of it. If you want to know something deep, you can maybe read more complicated definitions from various math textbooks, but for us this property is quite crucial, and in fact the first question is a very simple application of this property, and you will get the answers using that. Okay, so that's all I want to say about the delta function, and I think the lectures cover it quite well. Hopefully you will see more of it as we go along. Okay. So, if you move on to the other questions, the second question is once again an interesting and simple question. It is an intuitive question. It says, mathematically, what is the time required for the transients to decay to 0 for a linear system? Okay, so this is a mathematical question, not a practical question, and it is linked to the following question. You have this decaying exponential e power minus t. Okay. Mathematically, when does e power minus t become equal to 0? So, more or less that is the question that is being asked here. Think about it and ponder about it, and you might get an answer. Okay. So, that is the hint for the second question, and as you go through, you look at the third question. From the third question on, you will start getting circuits. Okay. So, there will be a circuit and some initial conditions, and something would happen at time 0. You will have to write, you will have to solve the circuit in some form and answer a question. For instance, this question says there is a battery, there is a switch, and there is an RC circuit. There is a resistor R and a capacitor C. Okay, and the question says Vc of 0 minus, the voltage across the capacitor just before the switch got turned on was 6 volts, and the battery is 20 volts, etc., and you are supposed to find Vc of t, which is the voltage across the capacitance as a function of t for t greater than 0, and write the answer. So, this requires a solution. From your experience, you might know this e power minus t by RC will show up in the answer, and what exact form it will take one can find by knowing the initial and final conditions. So, if you know the initial and final condition for the voltage across the capacitor, you can plug it into each of these answers and you will get the answer right away. So, that is the basic hint. You can use the initial and final conditions for the voltage across the capacitor and you will get the answer. Okay. The question number 4 is again another circuit, and once again all circuits one solves by writing the loop equation or a node equation, and by using the basic equations connecting the current and voltage across a capacitor. or an inductor. Okay. So, if you have an inductor L, the voltage across the inductor is L di by dt, right, where I is the current through the inductor. Okay. So, that is the first definition. Of course, for a resistor the property is very simple, voltage across is R times I, okay, the Ohm's law. For a capacitor, the current is C times dV by dt. Okay, the voltage across the capacitor is V, then the current is C times dV by dt. You use these equations, and of course for the voltage source the voltage remains a constant. Okay, so you use these equations relating the current and voltage of every circuit element, and then you write node equations or loop equations and you solve them. That is the way you solve circuits. Here is a simple example. It says in this circuit the voltage across the capacitance is given as a function of time, and you are asked to find Vs of t. Okay. So, now you can use what I told you, and then you can write down this expression. The voltage is given in terms of the ramp. You might want to use properties of the ramp carefully and get your answer. Okay. So, that is the hint for question number 4. Write loop equations, write a loop equation and use the equations relating the current and voltage of circuit elements. You should be getting the answer. Okay. There are also other things you can do to eliminate some of the wrong choices. If you want to do that, that is fine. Okay. So, the fifth question is actually quite a complicated question. We have, as you can see, we have given 3 points for it, and it is very difficult. I mean, I can tell you even now, if I start solving this problem, if I start writing out equations to solve this, it will take quite a while, and one needs to do some fair amount of algebra before getting to the answer. So, the question number 5 is a difficult question, but the method is exactly the same. You have a circuit with circuit elements, and there are there are 2 loops here, and you have to write loop equations. You have to be mindful of how the loop equation will show up and solve for the unknown. So, here the I1 and Vs have to be related. Vs is the voltage across the voltage source, and I1 is the current in the first loop, and you have to relate I1 and Vs. And it is possible you have to write down the equations, and there is a hint that has been given. Use some symbols for d by dt, d square by dt squared, and then d inverse for the integration, and you simplify, you will get to the answer. I am not saying it is very hard, but nevertheless the algebra involved is a bit intense. So, you write 2 loop equations and solve it, you will get to the answer. Okay. So, this is a slightly more difficult problem. It carries 3 points. So, the sixth one is a discrete time system. So, the reason why we put in this question is to just show you in one way how easy discrete time systems are compared to continuous time systems when you try to solve them. So, if you look at this equation, it says the input output relation is y of n minus 4 times y of n minus 1 plus 4 times y of n minus 2 equals x of n, and the input 2 power n is given for n greater than or equal to 0. So, what does that mean? X of n is 2 power n times un. Okay. So, that is the meaning of the input, and then the initial conditions are 0. So, what does it mean? Y of minus 1 is 0, y of minus 2 is 0, and so on. Okay. So, now you have to find the output of the system at n equal to 3. Okay. So, that is it. You plug in n equal to 3 here, you will get something, and then plug in n equal to 2, plug in n equal to 1, plug in n equal to 0, you will get to the answer. Okay. So, you just repeatedly use this equation, you can find the answer without any problem. So, the discrete time system, at least for the initial part, just solving for a few inputs and outputs, it is quite easy, and it is very simple substitution. Okay. So, the 7th question involves a little bit more complex ways of solving circuits. So, in this problem a switch remains closed for a long time and then it is opened. So, it is closed for a long time. So, the L1 inductor will have some current flowing through it at some time, and then suddenly there is in a loop another inductor is introduced after t equal to 0. Okay. So, there is a detailed lecture in the lessons about such things, inductor loops and capacitor loops, and how to go about doing them. It's there will be some discontinuities. You have to think of that method very carefully. This question is very similar to the method that was used. This question is very similar to one of the solved examples in one of the lectures. So, you go back and look at the lectures closely, you will see what to do. It is not particularly hard, but it is an interesting problem, and hopefully you will be able to get to the answer. Okay. So, this involves node equations, but you have to pay particular attention to the initial conditions, what happens from 0 minus to 0 plus. There will be some impulsive scenarios, and you have to pay attention to that, and you will get to the answer carefully. Okay. So, that is the hint for question 7. And question 8 is on convolution. Okay. So, in electrical engineering, particularly in systems, one cannot emphasize the importance of convolution more. Okay, so it is one of the most crucial operations that one needs to study in various forms. You need to be very comfortable with the basic notion of convolution, how to convolve two signals, various properties of it, how to think about it. All these things are very critical. So, I would suggest doing as many problems as possible in convolution so that you become really familiar with it. So, this question asks you to check various things, and a word about the notation in convolution. One needs to be very careful. When I write y of t is x of t convolved with h of t, it is slightly complicated. You have to think of x of t as a function for all t, and you have to think of h of t as a function for all t. Now, convolution is an operation which involves these two functions and then these two functions for all t and solves for the answer y of t. Okay. So, let me emphasize, let me write up something for this, just to still tell you what is how does this work. So, look at convolution. Okay. So, if you want to write x of t convolved with h of t, you could write it in two ways. Let me write it in one way, minus infinity to infinity x of tau h of t minus tau d tau. Okay. So, normally if you take an operation, so for instance, if I write an operation, I am sorry, let me write it once again. If I write an operation x of t multiplied with h of t. Okay. Now, if you write an operation x of t multiplied by h of t, to find the result of this operation at time t, I only need to know the value of x at time t and value of h at time t. Okay, only values at time t. You take those two values, multiply, you will get the answer. But convolution, even though we write it like that, x of t, h of t convolved, it is not enough if I know values of x only at t and values of h only at t. No way, you cannot find the convolution that way. This is just a shorthand notation to denote this complicated integral, and this integral, as you can see, uses the values of h and the values of x for all time. Okay. So, this notation is very misleading, particularly when you write x of t, h of t. It looks like you are using the values of x and h only for t, but that is not true. You are using the values for all t. You are treating this as a function of t, the full entire function of this. So, this star is more like an operator on functions. Okay, the entire function x of t is operated with the entire function h of t by convolution to get this answer. Okay. So, what you get here is also a function of t, right. Okay. So, when I say x of 2t convolved with h of t, what does that mean? I have this function x of 2t, I have to take that entire function and convolve with h of t. Okay. So, sometimes it can get a little murky as to what I mean. So, you have to be very careful in how you put this thing in and evaluate it. Okay. So, this question in particular will test your understanding of how functions are written, etc. Okay. So, it tells you if you look at the first option, for instance, if you convolve the signal 2 times x of t with h of t, what will you get? Will you get the signal 2 times y of t? That is the question. The first part of this 8th question is asking. Similar question for part 2, 3 and 4. Okay, the 4th one is a little bit different. It says, is it always true that y of t is equal to y of minus t? Is it always true that y of t is even symmetric? If you just convolve two signals, is it true that you will get a even symmetric signal? And think about it, and you will be able to answer some of these questions. Okay. Now, 9th is once again a simple question on convolution, but this is something you have to really master. You should know when you convolve two signals, what should you do? There is a series of steps that you have to do. You have to do something first, and then something next, something third, something fourth. There are 4 steps in that, and the 4 steps are multiplication, shifting, flipping and integration. Okay. In what order do you do them is the question, and if you know the definition, you can look at it closely and you get to the answer. Okay. So, the 10th question, okay, so 10th question is kind of an illustration of why impulse response, why LTI property, why convolution, all of them are really crucial. Now, if you take a system, you want to describe the system, I was mentioning in one of the previous lectures that the input output relationship is a complete description of the system. How do you find y of t for an input x of t? So, quite often the system itself you may not be able to analyze all the things that actually happen in the system, and finally you may not be able to write down y of t as a function of x of t. That might involve really complex arithmetic and all kinds of calculation. I was just mentioning the previous circuit which had 2 loops, and you have to find I1 as a function of Vs, and you would have seen how hard it is to do those manipulations. So what is desirable is some nice property of the system that you can exploit and come up with very simple descriptions of the entire system. And as it turns out, impulse response is one such powerful idea for LTI systems. So if your system is linear and time invariant, if I tell you what the impulse response of the system is, you can find the output y of t corresponding to any input x of t, and that is done by convolution. Okay, y of t is x of t convolved with the impulse response h of t. This is the critical and crucial idea, and why we study LTI systems, why LTI systems are so popular for analysis and all that. Okay, so this is very crucial. And if you look at question number 10, again it describes an LTI system through the impulse response. It says there is an LTI system whose impulse response is like that, and you're given any other input signal, you have to perform the convolution, get to the answer. Okay, so it's quite nice to see how this is done. And question number 11 is practice for convolution. Okay, so there are signals defined there, and you have to do the convolution, and you have to do the 4 operations in a certain sequence, and you get you get the value. We've asked you to evaluate the convolution at -3, -1, 0, 1 and 3, and you have to do it carefully, get to the answer. I believe this should be okay enough. Just as a motivation for you, if you're interested in a slightly more difficult convolution, I would urge you to try the following. Okay, so this is I should say it's a slightly more difficult convolution. Can you convolve these 2 signals? One guy is like this, is 1 from -1 to 0. Okay, it's a square pulse. It's 1 from -1 to 0, 0 elsewhere. You might want to convolve this with this signal, which is again 1, but from 0 to 1. Okay, so if you convolve these 2 guys, what will you get? Okay, so it's an interesting question. You might get a fairly surprising answer, but this will test your grasp of how convolution is. If you can do this convolution quite well, I think you're doing okay. Okay, so this is good practice. I would encourage you to try this convolution and practice, see if you've understood the operations quite well. Okay, so let's go back to the assignment questions. So this is this question just as basic convolution, and once again you come to the 12th question, which is again a classic question on LTI signals, LTI systems. You have an impulse response h of t, and now you have a slightly more complex input signal. It's delta of t plus 3 times u of t, but you know this is an LTI system, you can use so many different properties and convolution, etc., and you get to the answer quite easily. It's a standard LTI system question. And the 13th one is also a pretty standard LTI system question. You have the impulse response, you have the input. I mentioned the property of how to find the output. It's a convolution, and here you have these delta functions and unit steps showing up, and these kind of questions build up your comfort in dealing with delta functions in calculations. So how do you do convolution with delta functions? How do you do convolution with delta of t plus 1? Okay, there's a property of the delta function which was described in the lectures. You can go ahead and use that and solve the problem. Okay, so this was a short video on hints for solving assignment 2. Hopefully this hints will help you to go ahead and look at the assignment 2 questions once again in a different light and score high marks in assignment 2. Thank you very much.